All right. Thank you, everyone. Thank you for joining us for this another exciting session of BrainX Community Live, the October 2022 edition. For those who are joining us for the first time, this community was formed around 3 years ago. You see the picture over there, started with a small group in a room with the idea that we need to have this platform for machine learning in healthcare for good to enhance collaboration, to help everybody learn what are the opportunities for application of AI in healthcare. And now it has grown to be 4,000 plus member international community with some very active participation, especially on our LinkedIn group, which has grown to be 2,200 plus members strong, and a lot of content that we have made available thanks to all the people who have participated in this community over the last few years, as on our website, and then through these live sessions where we have the opportunity to have some live interaction. And thanks to some of the AV enhancements that have come about, we had actually gone to Zoom even before the COVID pandemic hit because there was such a demand from international community that they wanted to either participate or be able to see these sessions later on. So thank you. This is our webpage. For those who haven't visited there, this hosts all the content. It's not behind any firewall, so you don't need any login or password for that, but please enter your email address to join us there so that we can send you updates. And it has a lot of different areas of content. So we have our homepage where you can see all the updates about different content medium that we have had, whether it's podcast or interesting new article or upcoming session. The connect section that we have on our website is about our live sessions, which get recorded, and we have our own YouTube channel. It's called BrainX Community YouTube channel. So please subscribe us so that you can get the feeds as soon as they're posted. So if you miss something, you can watch it and you can get notification of that. As I'd mentioned, please join us on LinkedIn, a very active group over there. We share a lot of scientific work, opportunities to collaborate, opportunities to meet at different conferences. And then we have the Learn section, which has a list of curated articles. These are curated and classified based on the different specialties that they belong to, the healthcare specialties that they belong to. So these are categorized, you can filter them, you can search them, and that's where you can find one of the articles that is going to be presented today. So stay in touch with the latest and specifically for any specialty that you would like to learn more about. We have a very popular journal section because there are a lot of journals now for AI in healthcare. They're very focused on AI in healthcare. So if you want to know which journals you should be looking out for, you can go and filter our Learn section and find those journals and their listing and follow them. We have had a book section within the Learn, so you can filter our Learn section for books, and you can find some really interestingly reads which will enhance your knowledge. And of course, everyone is looking for data to do AI and any kind of AI modeling. You need data, and we have created one of the largest repositories of open source healthcare data sets. So we can't provide you the data directly. These are links, but these are again classified based on healthcare specialty. There are brief introductions about what's there in the data. So you can use your Google Colab or Jupyter Notebook and start using these open source healthcare data sets to build your state-of-the-art models. And we are all here to learn from each other's. We want to learn from each other's experiences, especially from those who have been leading this field. So you can listen to our podcast series called BrainX Talks. You can subscribe it in your favorite content medium, whether it's Apple or Google or Spotify, and you can get the latest podcast delivered to you by some of the esteemed speakers. Now that hopefully the COVID pandemic has settled, there is an opportunity for us to interact in person. Of course, many are still virtual or hybrid. So we provide a listing of upcoming conferences so that we can all collectively meet there, exchange ideas, and learn from each other. And every year for the last 4 years, we've been publishing a year in review. So this is a great place where you can look at your healthcare specialty specific research work that has been done, pretty extensive. It's open source, available through ResearchGate. And today we are going to talk about neurology. So you can look at the neurology list of publications where a lot of work has gone in using EEG waveform and trying to predict various different disease states, as we're going to learn from our speakers in just a moment. And of course, we're going to talk about seizure detection, and we are going to learn about some exciting extended reality solutions that can help us in healthcare and how AI is helping that too from our esteemed speakers. So we have Dr. Christopher Newey. He is the medical director of neuroscience ICU at the Cleveland Clinic Akron General Hospital, an esteemed colleague of mine, an intensivist over here. We have Moin Amin. Dr. Amin is a neuroimmunology fellow, also at the Cleveland Clinic. He will be joining Dr. Newey in talking about the publication that was based on seizure prediction. And then we have Dr. Joe Morgan, who's an anesthesiologist and the founder of Wear Health, a great friend of ours. And he has great interest in extended reality. He has built some amazing solutions for application in healthcare. So stay tuned and please post your question and answers and your comments in the chat session for the speakers, which we'll take at the end. So with that, I'm going to invite Dr. Newey and Dr. Amin to make their presentation.
Great. Thank you for that introduction, Dr. Mathur. Can you see my slides?
Not yet.
Okay, let me upload them again. How about now?
Yes.
Excellent. And let's show my video. Great. Yeah, so here I am. So yeah, thank you for joining us tonight. I'm really excited about this project and very passionate about it. If you've ever met me or talked to me or with me, I'm always talking about seizures and EEGs and how it's such an important aspect of what we do in the neuro ICU and how we monitor patients. And to me, they tell a story. This is something I've been doing for about 15 years or so, and it just really tells a story. And been collecting data for that time and really just analyzing it and trying to clean it. And it wasn't until Dr. Amin and I met up that he was able to take it to the next level, and I'll let him explain that next level when we get to that. But what I wanted to do is just kind of give you a little bit of the background first about what the issue is, what the problem is, and finally let Dr. Amin kind of take it from there and just tell you the solution that we are working on. So today we're talking about personalized model to predict seizures based on dynamic and static continuous EEG monitoring data. We have no financial or conflicts of interest to disclose. So the problem that we always have is clinical suspicion of seizures is not always correct. We've looked at this in many different avenues, and this one study here showed that about 30% of patients admitted with who had epilepsy or not were actually misclassified. So it's about a third of patients are actually misdiagnosed. And what we also learned is that seizure-like movements are not always epileptic. And just because you move, you act like you have a seizure activity, doesn't mean it actually is a seizure. This was seen in about another study in neuro ICU, and they found about 73% of patients who had some sort of epileptic jerks or movement disorders were actually not seizures. So it is a problem. And what you can imagine is if since someone has a seizure and you get placed on the anti-seizure medicine, and how that can be a lifelong event and how it may not be appropriate. And on top of that, you may not be classifying seizures correctly and you'd be missing them. We looked at our database over here about 8 years or so. What you see is that as we continue our monitoring at the Cleveland Clinic, the red bars, and on the bottom at the x-axis is the years. But as we increase our monitoring of our EEGs in patients, what we notice that there is an increased number of seizures we're finding. So the more monitoring we're doing, the more we're finding. The thing about it, we're also finding more non-epileptic events, which we call paroxysmal events, those events that do not have seizure or EEG correlation. So we have been monitoring more and more, and we're finding out more and more people are moving that don't have seizures, and more people are having seizures that aren't not really moving. So it's something fascinating. So really, we're missing a bunch of people. So one of the questions that we always keep coming up with based on this information is that, can we target who to monitor? We don't, for example, can you say that person that comes in through the ED to an ICU or the floor, can you say this person needs to be on the EG, this one does not? And that's something that we've been toying with in our head for probably about a decade now. And we've been looking at data regarding this. And so what we did when we first started looking at this problem, we found that about the majority of our patients that were on EEG had non-convulsive seizures. So about 20% of patients had seizures on the EEG, and the vast majority had seizures that were not seen except on EEG. There's no movement activity or anything that we would have known otherwise. So unless you're on EEG, you're missing a lot of people's seizures. The other thing we notice is that there's certain data that seems to have a meaning when we're looking at seizures. For example, there's some clinical data such as, why is a person being monitored? What's the brain injury? And the other thing is, what's the level of consciousness? Such as, are they awake? Are they lethargic? Are they in stupor or coma? Just keeping it brief there. But we also started noticing that maybe EEG patterns are predictive. And this is where we really want to take it, but I'll talk about everything else leading up to that. And the other thing that we also known or we notice is that if we have all the people as seizures and we map it out from the time from onset to the time that we notice seizures, what we found is that if we do not monitor people for up to 24 hours to 40 hours, we are missing a lot of seizures. We do not feel confident that we're catching seizures unless we monitor for 1 to 2 days. So again, it is a technique and a device that you need to have resources for, and it takes a little bit longer to monitor than you realize. So when we look at the different etiologies of why people may be monitored, we found that certain etiologies seem to have predictive values here, like hemorrhage, ischemic stroke, tumor. We also noticed that the level of consciousness seemed to be predictive as well, such as the mental state decreases from awake, lethargy, stupor, coma, that the odds ratio for seizure prediction actually increased. So that patient's in a coma had an increased odds for seizure than that person's awake. So even their mental status seemed to be appropriate and important. However, the question we keep wondering is, can we target who to monitor based on pure EEG data? And this is something that we keep asking, and I think it's a good question. So I kind of want to walk through why I think this is important. And like I said, EEG tells a story. You look at EEGs enough, you can start saying it reads like a book. And it's a very dynamic process. The EEG that you read in the morning may be different than the EEG in the afternoon or evening. So like I said, why is this important? This is a little picture of our EEG reading room. As you see, every screen has a different EEG on, and there's only a few people there looking. So there's an opportunity there that you may be missing that real-time input. There's a lot of value in that. But also the other issues are, well, not every hospital has the ability to place 40 EEGs on. Or if you want to monitor everybody in your ICU, you may only have 3 or 4 machines and there's 20 beds in your ICU. It is a very costly resource to patients. For example, it can be up to $5,000 a day that a patient may be charged for these. The ICU EEG readers, such as the physicians who are reading or the tech readers, are not as robust, and it does take a little special talent to read ICU EEGs. EEG support staff, do you have techs available 24/7 to hook someone up? And lastly, and like I said, I mean, do you have the devices? Do you need to start saying, this person needs to be on the EEG, this one does not? I've got a patient coming in that needs an EEG. Who can I take off? And these are questions that we are always asking ourselves, and we're hoping that as we gather data and experience with our EEG risk or seizure risk, that we can start saying who can come off sooner than later. So just kind of walk you through some EEGs. I'm not going to teach you EEGs today, but I just want to give you an idea of like the dynamics, what it looks like over time. So here's just normal EEGs. And you can see how even normal EEGs can look very different from what time of the day you look at. Then if you start looking at the slowing that you may see on EEGs, you can see even the slowing can look different depending on what the patient's doing or what the patient's brain injury is or how sedated they are. And even go any further, that slowing can even become more slow. And it just, it's a very dynamic process that can happen. One patient can look like this earlier in the day, and then later in the day look like this. So is that predictive? And the other thing is, what about the periodic patterns? Those patterns that may just have some sort of abnormal firing that we just don't know a lot about, but it seems to be abnormal, but maybe predictive as well. And even those patterns can look different from patient to patient. And finally, what about the sporadic epileptiform abnormalities, such as little sharp waves here and there, as you see here where I have highlighted in red? It can look different in different patients. Some can be on the left side, some can be on the right side, some can be more polyspike activity. And sometimes those sharp waves can be periodic, where they happen at a regular interval. And this irregular interval may have a more sharp appearance, such as here where I'm highlighting. Or on the first slide, you can see a little faster activity on top of the sharp activity. So a little overriding fast. So even then, those sharp waves can look different depending on the patient. And this led to a lot of discussion over the last probably 10, 20 years, is that maybe there is this ictal interictal continuum where these different patterns on the EEGs are meaningful, whether it's more ictal or less ictal. And even still, they just keep talking about this. Even the frequency of these patterns that we're seeing seem to have input. So just because you see, let's say this older terminology, pledge proper at, let's say 1 hertz versus 2 hertz may be predictive. And this is indeed what we found in our research when we started looking at this, is that these lateralized periodic discharges, or PLEDs in that older literature, seems to have predictive value. And this is really what got us thinking that EEG waveforms are predictive, whether it's blunted delta, overlying fast, that rhythmic like we talked about, just sharp. And even still, when we go through these, that those seem to have increasing odds of seizures based on the patterns. And indeed, some other patterns are being recognized as well, something called SERPID, stimulus-induced rhythmic periodic or ictal discharges. And this other one called brief potential ictal rhythmic discharges, or BIRDS, which may just be rhythmic patterns or short seizures, may also be predictive as well. And there's a lot of data coming out talking about the risk of seizures with these different patterns. And indeed, one of the papers that came out a few years ago was trying to take a lot of this data and make a scoring risk score based on these different patterns, but also had some clinical findings too. And they called it 2 helps 2B. As you see over here in the table, it's based on frequency of more than 2 hertz, sporadic epileptiform discharges or sharp waves. You have these lateralized periodic discharges or bilateral periodic discharges, or lateralized rhythmic delta activity, which is just slower patterns, plus features, which is a feature of like the overriding fast, for example, I mentioned earlier, having a patient with a prior seizure, or that BIRDS that we talked about are called brief ictal rhythmic discharges here. And based on that, you get a score, and that score can tell you a little bit about your seizure risk. And this seems to be validated. One of the issues that a lot of us have with the score is that it includes clinical data. Includes that you have to know if the patient has a prior seizure, for example, and sometimes it's a little challenging, especially if you have a comatose patient coming in. Includes data that many would call seizures. A lot of these brief ictal rhythmic discharges are just short seizures to a lot of people, and they actually may be classified as seizures. So it's not very clean. And also the last thing is includes data some would not consider ictal. That lateralized rhythmic delta activity still has a lot of debate. There's a lot of information that we need to gather about that still, but but the thing that we really liked about a lot of this is that it seems to be intrinsic to the reader. For example, if I'm reading a EEG the same every time, and my partner is reading it similarly, but let's say we're reading it differently than another institution, which happens with EEGs. But if you have a seizure or a risk model that was intrinsic to how you read, that would be more robust. And that's something that we were kind of hoping to create, is that having a model that's based on the reads that you're doing or that we're doing. So it could be interpreted at different institutions pretty cleanly. So I'm gonna let Dr. Amen take over from here.
Great, thank you. Let's see, Mike. Just going to see if I can. Oh, there we go. Perfect. So to address this problem that Dr. Nui mentioned with the large amount of EEG data that's available, and we're trying to make sense of it and trying to use it to predict seizure occurrence, I think this everyone would agree that this would be an ideal problem for machine learning or artificial intelligence to come in and help us make sense of this large number of data that's available for us, especially when it comes to continuous EEG monitoring. So we decided to build two different sets of models to answer this question for us and help us going forward, see if this approach is going to be successful. And you can imagine you may be able to tackle this problem from different angles, trying to predict seizures from EEG patterns. But we wanted to build something from the basic and then provide the proof of concept model, which we can then build on later on and make it more sophisticated. So for the models that we tried to create, we decided to build a static model, which essentially looks at the EEG pattern that a certain patient has had for the prior 72 hours as a binary presence or absence of certain features. And we wanted to take it a step forward as well to see if we can improve this model by adding a time component, meaning that does the day-to-day, does the dynamic changes over time, does that also come into effect? Is that also important in addition to just presence or absence of these EEG features or not? And then that led to our dynamic EEG model, which I'll explain a little bit further. Our inclusion criteria included, we looked at EEG records from 2010 to 2019, and we included adult patients between the ages of 18 to 90 years old. And the data that we extracted from this, again, you could look at the raw EEG, but we wanted to build a model that was based on the EEG reads at our center. So we actually extracted the classifications for those EEGs during each epoch. And each epoch is typically a 24-hour period, except for the first one that could include an initial 20-minute period. So these were extracted as a 0, 1 categories for absence or presence of each EEG feature, up to the point that the patient was had a seizure recorded by an EEG reader, human EEG reader. And we converted these EEG features also to the standardized terminology of ICU EEG, ACNS, ICU EEG terminology for it to be generalizable. And subsequently, what we did, let's go next here. And these are those. Oh, sorry. These are the 20 EEG patterns that were included. I'm just going to go back. Sorry. Dr. Nui, I can go back one slide on my screen. Sorry about that. Yeah, so these are the 20 EEG features that we looked at and we extracted from each epoch. And these are kind of the standardized terminology. And this is a flow chart of the number of patients that were included in our data set. And this is one of the strengths of our model, which was built on a large number of patients. As you can see, overall, we looked at, in the initial data set, there was around 41,000 EEG records included. And we had this problem of, an imbalance between patients without seizure and patients with seizure. And obviously, most of the patients didn't have a seizure who were included. So we decided to balance the data set by kind of randomly selecting patients from the without seizure category. And you can see the number of patients who are included in each model. And for each one, we tried to include at least 72 hours of prior data to build a model based on. So then the model is predicting seizure occurrence based on the prior 72 hours of EEG data available. And these are the performance measures of our models. So we built two models. For the static model, we used the XGBoost algorithm. which is a variant of decision trees. And for the dynamic model, we built a variation of neural networks called long short-term memory, or LSTM, which has a memory unit built inside of it so that you can use kind of time series data and use that time component into an addition of time component to prediction of seizures. And as you can see here, we were able to improve our model accuracy by building this, by addition of the time component there, and the long short-term memory unit network has an 83% accuracy in prediction of seizures based on the prior 72 hours of data available. And here's a how this model was built. So we selected patients who had up to 3 days of EEG data available, and each day was converted to a 20x1 array of those EEG features that I mentioned earlier, with 0 being the absence of those features and 1 being the presence. And if a patient didn't have full 3 days of data available, we just padded it with zeros. So if, for example, if they had 1 day only available, so it was pre-padded with zeros there. And then you built a LSTM layer followed by a dense layer and an activation layer to predict the seizure occurrence. And we also wanted to take it a step further. When it comes to machine learning, there's always this problem of understanding our algorithms. So with the XGBoost model, we wanted to also see if we can use the model to see how the model was predicting seizures. And here we use the SHAP algorithm here to try and kind of understand the model. And here are some of the features organized by their EEG features organized by their importance in prediction of seizures, as well as the direction of how they predict seizures. So as an example, you can see the NL, which stands for a normal EEG pattern, the high importance in predicting negatives or absence of seizure prediction, essentially. Whereas some other features, for example, sharp waves in SW here, had high importance, but into prediction of seizures, as you would expect. And we use this in action as well. So this is an example of this model live in action on 3 example patients, and how the model correctly identifies seizures. So in panel A, this was a 75-year-old patient who had a seizure within 72 hours of EEG monitoring. And the model predicted seizure because there was GPDs, continuous slowing, sharp waves. So these kind of overwhelmed the model into predicting seizures. Whereas in panel B, that's a 53-year-old patient who was monitored for the entire duration of EEG monitoring with no seizures. And then you can see here the blue, which is pushing the model into the negative or predicting not seizure. Those features kind of overwhelm. And then finally in panel C, that's a 67-year-old patient who again was monitored for the entire duration of EEG monitoring with no seizures. And again, the model was able to correctly predict that based on the EEG features. That's kind of all I had kind of explaining our model. So we think we can build on these models. Obviously these are kind of relatively basic models that build on 24-hour epoch. You can take it further with kind of looking at more granular time periods, in addition to hopefully at some point, actually reading the EEG in itself. The model hopefully can build sophisticated models that can even look at the raw EEG data and use those for prediction as opposed to our classifications. But there's a long road ahead, and we're pretty excited about this results, and hopefully we can take it further.
Thank you, guys. That was pretty interesting. I will take questions and comments for you at the end. We will follow up with Dr. Morgan for his presentation next, and we'll come back to have questions, as there seems like a lot of interest in this area. As we switch over to Dr. Morgan, I had a question about the gold standard. So what's the baseline in terms of prediction? So which most of the times in healthcare, it is the clinician who is classifying these. So when you, in this case, the EEG features were already there. They were labeled by clinicians, right? And so what's the baseline in terms of the gold standard for prediction using those?
You mean to predict seizures in themselves, like based on the,
yeah.
Well,
how good is that?
Yeah, I don't think we have a goal, and Dr. Newey can comment on this. I think at this point, it's the clinicians' expertise, really. We don't really have a sophisticated model that can accurately predict seizures based on. And Dr. Newey mentioned some models that have been built, like the model that he mentioned briefly earlier. Yeah, as far as I'm aware, there's no gold standard. And Dr. Newey can comment further.
Yeah, that's a really good question. That's actually like the holy grail, I guess. There's a company that's been working on this for probably 10 to 20 years, and they're still keep updating. It's getting better and better, but the gold standard has always been the clinician. The thing about where our data came from is that all the clinicians are board certified, and our EEGs are also always overread by more senior people. So there's a lot of robustness in our data set versus some other hospitals that may only have that. But that's one thing I really liked about this, is that it's the data. If let's say Moen's reading an EEG and I'm reading an EEG and he reads it a certain way over time and I'm reading it a little differently, this model is for that reason, is that it's based on how I'm reading it. So it takes the data I'm inputting and it's taking the data he's inputting. So if he's always inputting the same data and predicts the seizure, then so it was pretty robust from that standpoint. That's what I liked about it.
Yeah, standardization definitely helps there. All right, I'm gonna have it switch to Dr. Morgan and have him go ahead with his presentation. Welcome, Joe.
Hi, everyone. Thanks for having me. I really appreciate the opportunity. Can everyone see my slides? Okay, great.
Yes.
So my name is Joe Morgan. I am a practicing anesthesiologist and founder of a company called Wellevate. And Wellevate is the company, and we really go by Waya Health. We make extended reality solutions focused on patient care. My disclosure is that I am founder and president of this company. So my background, I won't read through every last bit, but I have known Piyush for a very long time now, and know Chris as well for several years. I have had past experience working with Anthony Chang's group at the American Board of Artificial Intelligence and Medicine. That's been a fantastic experience, and have learned really just an incredible amount over the last 6 years with this company. I did some work with controlled substance collection and disposal when I was a resident at the Cleveland Clinic, and really since residency, I've learned to develop extended reality experiences and play with AI models and really explore the integrations that are possible between these two sort of emerging technologies. I've also done some past consulting work in physiologic tracking and wearable devices. So just some definitions here. I won't read them verbatim. The most important thing to know here is that extended reality is really anything along the spectrum that combines virtual and or augmented reality. So just some key concepts for purposes of what we're going to talk about today. Modern extended reality would not, frankly, exist without advances in AI and computer vision. Computer vision is very much an enabling technology for extended reality, and that's just simply put, that's how you know where you are in physical space, and how you can have your movements correlate with movements within a virtual environment. These two technologies can be highly synergistic, and I think we're only going to see more and more of it going forward. And a lot of the considerations depend on the specific use case. That is a critical point to make, and it's absolutely critical to involve domain expertise and developers and communication between all parties from really inception in order to be effective. Data is extremely voluminous and robust, and you can fill up a hard drive very quickly if you're collecting everything possible using extended reality. And so as such, that's another sort of appealing thing within the AI community, because more data is always something that is sought. And for all practical purposes, perhaps the most exciting thing for me between these two technologies, extended reality can help convert artificial intelligence outputs, if you will, into clinical results. And that's for a couple of reasons that we'll touch upon. But to take a little bit of a side path here to just talk about technology and healthcare, and how we got to where we are today, and really come back to the points I was just making. I liken technology and healthcare to a hippopotamus, and it's big, it's fat, it's slow, and it's potentially deadly if you do it wrong. And I don't mean that in terms of a new company with a new idea per se. I also mean that in the context of our EMR doesn't talk to outside hospital EMR, or any number of things that we all run into almost on a daily basis in clinical care. And so, part of the motivation, certainly for myself and other physicians that were early members of our company, we really felt this frustration with that massive gap that exists between what's possible using technology and what finds its way into healthcare. And so, that was really one of the big motivations behind the genesis of our company. So, I don't need to preach to the choir too much, but move fast and break stuff doesn't work here. It's about being not wrong more so than, being 100% right. And, we have this constant need to do more with less. And so why, as I was alluding to a slide ago, why extended reality? Well, it has a very uncanny ability to achieve user engagement, to get people to work out, to get people to ignore their pain or do something in spite of anxiety, and so on. And it's really something that should not be taken lightly. This is not a cell phone on steroids. It's a completely different order of magnitude in terms of its effectiveness, and its sort of potency, whether that's for good or bad. Other elements that are really relevant here are immersiveness, the effectiveness of a experience or set of experiences does tend to correlate with the level of immersiveness experienced by the user. And another sort of central tenet, certainly that we've utilized as a company, is the fact that you can really control the spectrum of attention. Whether that's, we don't want the user to pay attention to anything in the real world, like right before a needle stick, for example, or we actually want to remove all of the noisiness of the real world and remove distractions so that they're able to focus on whatever's before them. And it's very attractive in that it follows a digital health model. And so it can really scale to help a lot of people with minimum increases in cost. Just making the point here that this is an extremely potent medium, and this is a paper that essentially was comparing, I believe it actually was EEG tracings, and it was between folks that were given awe-inspiring virtual reality experiences, and then comparing those tracings against people that were that had taken LSD, and they were unable to decipher which group or classify out which was which. And so that just gives you an idea at a very qualitative level how potent this medium actually is. And again, it can be used for good or bad. There's 30 plus years of peer-reviewed evidence for extended reality in healthcare, and so this is something to really keep in mind, and just have an idea that this is very real, that there are significant benefits that can be achieved. It's not a silver bullet, but there are a lot of significant movements that can be made using this technology. And there's utility in every specialty. And so challenges I've faced, challenges other people in our space have faced. Certainly internet connectivity, believe it or not, that is still an issue. I'm sure that's an issue in pure AI efforts as well. The typical hospital in the community is, layers upon layers of aging infrastructure, and as such, it's a very important practical consideration. There are institutional level issues and other things that we as clinicians certainly find annoying. But suffice it to say, I think it's been very rewarding for me. In 2017, we would go out and we would reach out to a nursing home or a hospital. We'd speak to them. We say we're using extended reality in healthcare, and they'd look at us kind of like, once they realized we weren't doing like anatomic education, they looked at us like we had two heads. And then, the last couple of years, that certainly has 180'd and people get it. And so that's been very exciting and rewarding for me to see. And these are just, the items in purple are really how we would address these things. And I'll just kind of go ahead to just explain what we do broadly and then really dive into the AI piece and how we're using it. What we've built is a system that combines three different elements. There's a cloud backend, a web application that's used by providers, and then we have a extended reality application and content library. And so, we're basically utilizing these elements to keep the providers engaged, to deliver diagnostics, therapeutics, assessments, and better tools for care using the medium of extended reality. We're in over 75 hospitals in almost every state, and we're growing. We've built a scaled solution for distributed healthcare. One of the most exciting things for me in terms of disruptive potential, to use a cliche, is really to remove a lot of those things that stand in the way of us as physicians, clinicians, nurses in caring for patients. So it's a technology that we can use to displace some of the annoying things in our daily lives, to get back to patient, provider, relationship, and all these things that kind of stand in the way of that, brush those aside or have them be handled by the technology itself. We have plenty of outcome data. These are some of the more exciting outcomes over the past several years, but there's plenty more besides this. We've shown significant reductions in anxiety, consistent and significant reductions in pain. Almost everyone indicates that they would recommend it to their peers, whether that's other patients or providers. And there's significant reductions in stress as well. We have an integrated telehealth capability. I didn't want to show another provider, so that's why I have myself on there. But this is just a demo picture. The point is, though, that we have an inter-reality telehealth capability. So I, using a web application, can kind of connect to somebody in virtual augmented reality anywhere around the world. So let's dive into the actual AI stuff. So, as I mentioned, computer vision is something that is an enabling technology for extended reality. And there are, I think, any number of different applications. I think the sky's the limit. And really, I think we're limited by two things. One is our own creativity. And then the other thing is sort of being, providers, the available time that we're willing to set aside. What you see before you here is actually a computer vision model. I got working on a headset. This is over 2.5 years ago at this point. But what I did was I kind of figured out a way to tap into the pass-through camera programmatically. And, this is obviously a black and white camera. And so, you have an appreciation that this is something that was from a headset two headset generations ago now. But what I was able to do is actually get a lightweight object detection model and get it running on the headset such that I was able to detect objects in the real world and have them register and logged and so on and so forth. And you can really start to think about how these things can really make a practical difference. You know, if it's 2 a.m, maybe I shouldn't drink that cup of coffee. Maybe I should lay on that sofa, or, you know, maybe there's, you know, a big sugary candy bar. And if I'm a diabetic, you know, knowing where that is and knowing that I should avoid it, you know, would be very useful things to do from a health standpoint. Natural language processing, obviously interactions with avatar therapists and things, but I think one of the other sort of realms within NLP that I find very attractive in terms of its marriage with extended reality is just this sort of fly on the wall technology, fly on the wall approach for using it as a biosensor, meaning that, you know, the overwhelming majority of wearable devices and physiologic trackers find their way into the sock drawer within 6 months and they never come out. And so as such, you know, just having somebody partake in an extended reality experience and using NLP and various other different capabilities to you know, determine various different health properties and features of an individual using the technology, I think is really attractive. You're not asking them to do anything, you don't need them to do anything, but then it at the same time provides very useful information. I think recurrent neural networks are actually one of the biggest items in terms of things that are overlooked and their potential for applicability within extended reality for healthcare. And that's simply because RNNs are very useful for time series data. And, you know, when somebody's using a headset, you know, we call individual scene or environment a scene. And then any one continuous use of the headset, whether that's one or more scenes, we call that a session. And so, of course, all of this happens as a function of time. And so, you know, watching various different parameters change over the course of a session is certainly useful information. Reinforcement learning and its sort of antonym, adversarial learning, rewards and punishments, and essentially, you know, rotely iterating through, you know, millions or billions of different iterations of potential possibilities within a simulation environment very much lends itself to extended reality. And frankly, that overlaps with one of the other sort of, you know, sexier terms as of recently, and that is, you know, synthetic data production. And, you know, these are things that are actually using extended reality to help AI, whereas most of the other things I've been talking about thus far are AI to help extended reality in some sense. Multimodal approaches, so combining all of these different things, and I call your attention to the lower right-hand corner here, which is really just a landmark paper that I've read probably 5 or 6 times, and you know, I still don't understand a lot of it, but the more I understand in it, the more I'm blown away by it. And it was written by Ian LeCun, who's, you know, a real leader in artificial intelligence. And really what they're kind of going towards is, you know, a model that, you know, would function like a human being. It doesn't map to the human brain or anything like that. The point is that it behaves as such. And, you know, as scary as it might be, you know, LeCun and a bunch of other leaders are working at Meta, and, you know, I still maintain my position that if you look at Meta's research lab and their code and what they produce, they're in many aspects kind of ahead of the game. And so I would encourage you guys to read that paper, A Path Towards Autonomous Machine Intelligence. And so just getting into what have I done, I'll show a quick video here. It's a little over a minute, but this is one implementation that is beyond that sort of very basic thing that I showed with the image recognition. And this is something that, you know, we have developed. It's been around for, this version has been around for about 6 months, and we have a newer version coming out that we're very excited about. So I'll just let the video speak for itself.
so many others with dementia, my mother, who suffered from Alzheimer's disease, died alone by herself in a nursing home due to coronavirus in 2020. Prior to going into the nursing home, I had a chance to share virtual reality with my mother. At the time, she still really wanted to go back to Italy, and this was the chance to do that for her. I still remember the joy that this brought. I still remember the smile on her face. And we want to be able to bring that to everyone.
And so, what that is it's simply something that can take people where they want to go. And when we started to look into this as a company, we ran into problems with, okay, if we're gonna, have 360 videos of everywhere, you run into a couple of issues. Number one, if somebody wants to go somewhere where you don't have a video, it doesn't work. And we're not Google. We're not going to, have cars going around the planet and filming everything possible. The other thing is that you run into a very pragmatic issue, which is, if I take a picture of the Eiffel Tower or something, and somebody's building's in the background, then you run into this morass of potential copyright issues, and you're taking pictures of my stuff and so on and so forth. So this was a very interesting way to achieve the goal of not running into copyright issues, and also having something that is capable of taking people, whether that's in a photorealistic way or a more of an artistic way, to the various different places that they want to go. And so with that, I'll just mention in closing that it's really worthwhile and valuable to view extended reality, not as a headset or a game, but think about where it's going in the context of healthcare, and think about it as a diagnostic lab, a digital pharmacy, an enabler of a really a very capable type of telehealth, and a digital administrator all wrapped up into one. And so what does that do? It empowers you, the provider, to better care for patients. And so that's our vision. That's what we're doing. And thank you so much for your time.
Thank you, Joe. That was definitely very, very exciting. And I think for both the group of speakers, it's some amazing stuff that you're doing. I'm going to take some of the questions that were here in the chat. One was from Raji. Raji, you're here. Do you want to just ask the question? We're a small group. Do you want to unmute yourself, introduce yourself, and ask the question?
Yes. So yeah, I'm on the board of advisors for Global Health Impact Network, and I'm working on a startup to redefine the future of medical education and training worldwide. I put, in addition to the EEGs used with data sets that have been collected, Are there any other data points that are used in addition to the EEGs to, derive more meaning, additional blood work, AI-assisted radiology, patient history and EHR blood work, et cetera, stuff like that?
I could start, and you'll have more input too. I think that actually would be great if we could integrate it more with EMR at some point. Right now, we're just trying to keep it pure just from the EEG aspect, just so we can say the way you read and I read, it's very robust and really pure from that sense. As I've mentioned, two of the data things that seem to be a common theme that we found is the etiology of why they have brain injury. People don't realize like that sepsis patient actually has a higher risk for seizures. We see that in our data sets. And also just their level of consciousness. We've looked at different lab work in our prior papers, and at least in some of the prelim stuff that I've done before looking at this. I used to go through all the Apache scores, and I mean, I just get bunches and bunches of data. But nothing really seemed to pan out except for those two things plus the EEG waveforms. But who knows with more data, who knows?
Well, there is an additional question from Zeba Singh. I don't see her here. She might have left. It was about the model itself and whether it is when, let me read this, is the prediction made by the model when a patient is having the seizure, or is it predicting about a future seizure, that the patient is going to have a future seizure?
Simone, I'll let you talk unless you want me to answer.
Yeah, so the way we built this model was it was using the data up to the epoch where the seizure occurred, so not including the seizure epoch itself. So really it's predicting seizure that's going to happen in the next epoch, if that makes sense.
Got it. Thank you. And let me just go through the, by the way, I love the Shapley work. I think that is awesome. The explainability part of that definitely helps, and also helps build the individual predictions. So we have used that in the past, and that's been very good. I had a question for Dr. Morgan. So, Joe, where do you see this going specifically? Because there are a lot of applications that have been proposed in the past. So you showcase some of them, like anxiety reduction, helping patients with decreasing the need for sedation. Where do you see this going in the future? Where do you see some of the ripe application areas? Is it for seizure avoidance, so that patients don't get seizure and we don't need seizure prediction at all? Where do you see this going?
Yeah, so I think that there's going to be kind of a natural evolution. You know, the rate of acceleration within extended reality, broadly speaking, not just within healthcare, has somewhat been limited compared to, like, for example, just pure artificial intelligence on a computer, and that's for a very practical reason of the hardware bottleneck, right? It's another $1,000, you know, and these things are not as ubiquitous. Over the long run, I think that issue will take care of itself, and that you know, no one is going to carry around two devices. The mobile phone and the headset will be one and the same. So all of that being said, from, you know, I guess a macroeconomic perspective, I think between now and that point, I think where we're at now is a need for increasing awareness within smaller and community-sized hospitals. I think you know, we're at a point now where certainly all the major academic medical centers are, in many cases, not only aware but actively involved, which is great. And I think, you know, when is it going to really take off? I think it's going to be those use cases that show an increase in throughput and improvement in efficiency, a meaningful cost reduction by, you know, either avoiding certain medications or the need for a more expensive test now that we have a scalable, you know, digital test, if you will, and items that are frankly billable. The first CBT code involving virtual reality, I believe, is set to go live in January. So, these things are coming, and I think there's now a pathway to get there that's very clear. And I think it's really about finding those areas in which, not only can you move the needle, because I think extended reality can be used in a lot of different areas that it can make a significant difference, but it's almost like a level beyond that now, where it's like something that can also make an impact on a metric that, the administrative types really are concerned about. And we're getting there.
Sounds great. I think we will end it here. Thank you everyone for joining us. Just as a reminder, BrainX community has a whole host of content available through different medium. Thank you to all the speakers for a great session. We learned a lot. Thank you for the participants for the great questions and comments. This will be posted on our YouTube channel. So until next time, take care and have a good evening.
Thank you so much.
Thank you for having us.
Thank you, guys.